So I'm Fotini Koidaki. I'm working on the computational analysis of 19th century Greek literature. I use NLP methods, and I'm going to talk to you about what happens when you try to teach a language model to read and enrich novels, and what that process reveals about reading itself. There is a common perception outside our field, which is the interdisciplinary, that, as Maria said. There is this common perception that computational literary analysis doesn't involve much close reading. Computers find patterns, assign labels, and we end up describing graphs, that the interpretative work happens elsewhere or not at all, or even sometimes it's insufficient. And I want to challenge that, and I'm going to do it with 3 words. I don't know if I should mention again that I'd like to defend that close reading is essential part of distant reading, the so-called distant reading macroanalysis of literature. I'm not sure if it moves. Okay. Do you know this place? It's a place. There is a translation. The Faragi of Sfakion. It's the Faragi of Somarias, the Gorge of Sfakia here in Crete. I think that some of you have visited. Claude GPT and Gemini knows it too. And if you ask them, they'll reply about the history, the role of this place in Cretan resistance. But when they encounter this phrase in text, they forget it. They see only the Sfakion, not the Faragi. Why? And how do we what we have to do to make it visible again? And that's the talk is about. So, for those of you who were here last year, this is where we left off. We had fine-tuned a space model and a Greek bird to recognize the allocations, and we identified a core challenge to denote the entities between log, GP, and pair, because person names and the distinction between log and GP made a lot of noise. They bleeding into each other. The proposed next step last year was to bring in large language models. And this year, that's exactly what we did with an expanding schema with more data. The schema is called GeoEffect, and it's designed to capture geolocations, to perform the spatial analysis and capture the emotions related with the geolocations in persons. We evaluated 30 LLMs via few-shot prompting, and we created through gold set of 363 annotated sentences. As for the schema, when we study a literary corpus that shares common geographic identity, we want to capture cultural characteristics, and these are 4 entity types that are the most essential for us. The log gives the physical space, while the GP gives the political space. The NOP, national or religious groups, gives or political, the P stands for political, gives us the collective identities, peoples, nation, religious bodies, and the PER, the pair persons, is there for 2 reasons. First, because in practice, person names were creating a lot of noise, as I said earlier. And because person names, they are involved in emotions that I identified in text. These categories are not self-evident. Defining each one precisely requires us to read carefully the texts. So, the case of the Faragi to Sfakion, the Gorge of Sfakia. Why did the models fail? Not because they didn't know the word Sfakion, they did. not because they didn't know the word gorge. They did also, but they missed the whole phrase as a compound phrase. The model doesn't have access to the referent the way we do. The referent is, as we know from semantics and NLP, and is the word for the actual thing in the living world. So when we read Faragi, the head word, as it's called, we immediately connect it to a type of entity in the real world, a physical landscape that have depth and geography. That connection gives us the category LOC, location. The model doesn't make that connection. It has access to the syntactic and lexical behavior of words in the language. So when we wrote the rule to fix it, you can see the rule. We couldn't say this is the physical place, find the physical place. Instead, we say, when you see a landscape noun followed by genitive toponym of that is DP, tag it as location. And this is a compound entity. The moment of stopping in front of a phrase and asking, what kind of entity is this? And where does it begin? Where does it begin? This is the close reading. The syntactic rule is how we made that reading computable. So let's look some other of my rules. Each one goes in literary and linguistic judgment. You can see here the simplex annotation rules. I put them on the top because they are the first in my prompting, the final prompting designs. When a proper name of a natural feature appears, tag only the proper name, anything else. The landscape noun stays outside the span. And national adjective stands alone, elinikos, and I use the Greek word elinikos here because it's not capitalized. The first character is lowercase. This is NOP, a NORP tag. The cultural charge lives in this adjective, not in the nouns that it follows. Then there are rules for compound rules, compound samples. When we should know what we have to bring together when a natural landscape receives the genitive toponym, this is an entire phrase entity as log. Lake Michigan, for example. This is not a referent for the town, but for a lake. When national adjectives combined with administrative term, for example, Greek state, Elliniko Kratos. This is a GPE. And you can see below the head inheritance rule, which is very important in my schema, and perhaps is the most elegant. When two or more entities share the common head word, that may appear only one, they should share the same label. Nation of Greece, for example, and Italy. These are not GPs. These, in fact, are NORPs, people of Greece and people of Italy. Two NORPs, not GPs. I won't go into more depth here. These rules are enough. After all, writing the rule is only one part, the half part of the work. The other half is testing whether the model executes these rules.
Correct.
Yes, correctly, of course. So, about my technical setup, a brief note here. All models, certain models, were evaluated via API calls through OpenRouter, not chat interfaces, which ensures reproducibility and cost control. Every iteration was tested on the same 8 sentences, 8 samples, finalizing at a pool of 70 few shot examples, 17, not 70, of course. We also tracked cost and response time per model for each iteration, and there were hundreds of iterations, yes. And the temperature was set at 0.01 to minimize the output variability because we work with non-deterministic tools. And the prompts were developed and stored standalone as TXT files, separate from scripts. So the interesting part, the prompts. We built the prompts across multiple versions, and behind these versions are dozens and dozens of iterations, testing different rules, rule orderings, markup styles in prompt, indentations even, verbose vs minimal, as you see in the third phase, third version, verbose versus minimal structures, English versus Greek. What you see in this table are the best performing prompts from each version. Each version has many subversions, sub-iterations. You see the best result. The numbers go up, but that's not the interesting part. What's interesting is what had to change to make them go up. In version 0, we simply asked the model to find name entities. You're expert in finding name entities, and do that. Find this and this and this. In version 1, we gave it category definitions, but they were very generic. In version 2, we added boundary rules about the spans boundary. These rules didn't come from NLP guidelines. It was the rules like the rules we saw earlier. In version 3.3, we introduced compound entities and the chain of decision, very important, the chain of decision. This is a structured reasoning process embedded in the prompt, at the end of the prompt or in the beginning. We tested the position of the chain of actions that says find this first and then find this first and then GPs, and after GPs find this with sub steps inside. And here comes the interesting part, the revealing. The verbose version performed worse than the minimal one. 87 versus 92%, as you can see. More words, less clarity. It was exactly the same prompts, exactly the same rules. That itself is a finding about how these models process instructions. In version 4 and 5, we replaced 5 few short examples to strengthen the hardest cases. We replaced actually 4 few short examples, and we added 1 more. And this is how we ended up with 17 few short pool, which is okay. I should note here that testing more than 17 few short examples, it was not only more cost, but it made noise. It gave us poor results. So there's a limit in few short sampling. And in version 5, we reached 97.2 and 76 average, 76.6, just by reordering the commands in the chain of decision. Models execute rules sequentially. One label was eating the other label. So we reordered the chain of decision several times to achieve the best possible outcome. So I thought that this could be helpful, but if you ask a large language assistant how to write a good prompt, it will probably tell you to use XML tags, detailed explanations, add examples, add negative and positive examples, or add negative examples before positive examples. Well, in my case, this recommendation didn't work. I wrote the whole prompt in XML and it didn't work. The prompt is written in Greek, not in English. I tried the English version. I've tested. It is in Greek because the corpus is in Greek and the annotation guidelines are Greek. And switching languages in mid-process create a necessary overhead for the model. So proximity between the prompt and the analyzed text matters. The markup is lightweight, like loose HTML. No unnecessary blank lines, no blank lines actually, because blank lines signals a new section, end of something. And it's not good in the eye. It's not very good in aesthetic, the final prompt. And the capitals, when we need the model to treat something as a hard constraint, we use capitals. Never do that. The never word is capitalized. Always do that. Use capitals. We used to use capitals very wisely and avoid regular use of capital letters. These are not aesthetic choices, as I said, and no hedging, of course. Not these may be allocation or usually compound entities look like this. No, these. We need absolute formulations only in prompting. So, numbers here. The 13 models across all versions. You can see involved the best performance per model. I hope that you can see the bold. Let's go here and here. This is the best of DeepSeek version 3, F3. And this is of the Llama here in the large version of chain of decision here. And it drops and drops, drops. I should say that version 0, the prompt is very, very, very minimal, bare prompt. And version 1, I said earlier, has more details about categories. As the prompt goes and depth in knowledge and rules, it accelerates the cost of prompting and iteration. So, if you step back, you will notice that the general trend is upward. As the prompt becomes more refined, performance goes up, and the heat maps move from yellow to red to more green. But not uniformly. Some models respond strongly to every iterations. Others stops improving after a certain point. Look at Sonnet 4, for example, the first model, with the top candidate. No, because it has high prices. It's on the top and reaches 97.2 from the 4th version, but at a cost. For a task like this, run across hundreds of sentences and multiple prompts, version cost is not trivial. It's not trivial. And a few models like Mixtral and Gemma don't follow the curve at all. One case stands out. Mixtral drops from 51% to 19.7 at version 4, the version where we introduced new for few short examples. The prompt didn't break for anyone else, but for Mixtral, something in that structure triggered a catastrophic response. This is a reminder that prompt optimized for one model is not a guarantee that is good for other models. So let's see these lines of my top 7 models. The general trend is upward, but look what happens between version 3 large and version 3 minimal. Same rules, same content, same examples. The only difference is the chain of decision was stripped down from verbose to minimal. Most models jump significantly in the minimal version. DeepSeek R1 goes from 79.6 to 92.6. Gemini from 77.1 goes to 86.2. And this is my top candidate for the corpus enrichment. I should note that. Gemini Plus, it is very fast and has great potentials. And DeepSeek V3 from 70.8 to 87.3. But look what happened one step earlier at version 3. Claude 3.5, the haiku, and DeepSeek V3 both dropped from V2, the version 2. The verbose chain of decision didn't help them. It helped them. The same content that improved most models became noise for these two. And version 3 mini, the mini version, almost reversed that for both the recovered. Same rules, the information didn't change, the execution pathway did. So less prose, cleaner instruction, and the models perform better. This is not just a finding about prompt length. Clarity of instruction matters more than quantity of explanation. So let me return to where we started, the perception that computational literary analysis bypasses close reading. I hope that I've shown you the opposite by now. To recognize a gorge in 19th century Greek corpus, we had to articulate what gorge looks like in texts, and we translate that in a rule precise enough for a model to execute this. To tag a collective, we did the same. We had to define what collectivity looks like in text. To order a chain of decision, we had to understand how these categories relate to each other and which ones override which. That is close reading. Distant reading presupposes close reading, not silent, not intuitive, but explicit. Explicit enough to be encoded, explicit enough to run progressively in 30 models. Thank you.